Welcome to this deep dive, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we're jumping into Unit 13, Nuclei, and we are going to tackle a really fundamental and, frankly, a mind-bending topic, the true size of the nucleus. We'll keep it simple, exam-safe, and hopefully make it something you'll never forget.
This is one of those topics in physics that, it really challenges your idea of what solid matter even is.
It really does. I mean, we are taught that all the positive charge, almost all the mass of an atom, it's all packed into this tiny central point, the nucleus.
Right.
But the scale of it is just, it's hard to grasp. So let's start with a thought experiment. Imagine we could take a single atom and blow it up, expand it to the size of a big classroom.
Okay, like a whole lecture hall.
Exactly. Now, inside that massive room that represents the atom, how big do you think the nucleus would be?
Well, it has almost all the mass, so I would guess maybe like a cricket ball or maybe a small apple rolling around in the center, something you can see at least.
That's the logical guess. But here's the crazy part, and this is straight from NSERT. If the atom is the size of the class M, the nucleus would only be the size of a pinhead.
A pinhead? Wait, seriously? In an entire room?
A tiny, almost invisible speck. That's it.
Wow, so the difference in scale must be huge.
Yeah.
That means the radius of the nucleus is just tiny compared to the atom's radius.
It's colossal. The radius of the nucleus is smaller than the atoms by a factor of about 10,000.
10,000 times smaller.
Yes. And think about what that means for volume. Volume goes by the cube of the radius, right?
R cubed.
So the volume of the nucleus is about 10 to the power of minus 12 times the volume of the atom.
10 to the minus 12. That's practically zero. So the atom is, it's almost entirely empty space.
Almost completely empty. It's a vacuum with this one impossibly heavy speck at its heart. And this is what leads to the density shocker. This pinhead contains more than 99.9% of the entire atom's mass.
So all that mass is crushed into that tiny, tiny volume. The density must be astronomical.
It is. If you could somehow take just 1 cubic centimeter of pure nuclear matter, that's about the size of a sugar cube.
Okay.
That little cube would weigh around 100 million tons.
100, sorry. Do you say 100 million tons?
100 million tons. It's like taking Mount Everest and crushing it down until it fits into a sugar bowl.
I can't even imagine that. How is that even possible?
Well, that's the power of the strong nuclear force, which we'll get to. It's the only force strong enough to hold matter together under such insane conditions.
Okay, so that really sets the stage. This brings us to the core idea then. What is this nucleus, fundamentally, and why is its size so important?
The core idea is actually simple. The nucleus is just a tiny, unbelievably dense ball of protons and neutrons. We call them nucleons.
Right, nucleons.
And its size, which we measure in femtometers, that's 10 to the power minus 15 meters, is not just some random number. It's absolutely critical.
Oh, critical for what?
For stability. That femtometer scale is basically the operational range of the strong nuclear force. If the nucleus got any bigger, the strong force wouldn't be able to hold it together against the electric repulsion of all those protons.
So the protons would push each other apart and the whole thing would just disintegrate.
It would fly apart instantly. So size dictates whether an atom can even exist.
Okay, but that brings up a huge question. The one Rutherford must have faced. How do you measure something that's 10 to the power minus 15 meters across? You can't see it.
No, not with any microscope. Visible light has a wavelength that's about 1,000,000 times too big. You can't see it.
So what do they do?
This is where we get the brilliant blind geologist analogy. Imagine you're blindfolded in a dark room and you have to figure out the size and shape of a big rock in the middle.
Okay.
You can't see it, you can't touch it, so what you do is you start throwing small pebbles at it from all different angles.
And you listen to how they bounce off, the angles they deflect at.
Exactly. You map the object by analyzing the scattering of your projectiles. It's like using sonar to find a submarine. And this is precisely what Rutherford did.
His pebbles were the alpha particles.
Correct. Positively charged alpha particles. He fired them at a thin gold foil, which is full of positively charged gold nuclei.
And since they're both positive, the alpha particle gets pushed away, the Coulomb repulsion.
Yes, and the closer it gets to the nucleus, the more strongly it's repelled and the more it deflects. By measuring those deflection angles, he could mathematically work backwards to figure out how close the alpha particle got.
So he could calculate the distance of closest approach.
Precisely. For a 5.5 MeV alpha particle hitting a gold nucleus, that distance came out to be about 4 times 10 to the power minus 14 meters. This gave him an upper limit. He knew the nucleus had to be smaller than that.
An upper limit. So he didn't measure it directly, he just put a boundary on how big it could be.
It was a deduction, a brilliant piece of scientific detective work.
Okay, that makes sense.
And just to really hammer home the scale one last time, if we say the nucleus is the size of a marble, about 2 centimeters,
Right, a marble in the center.
then the electrons, which define the edge of the atom, would be orbiting as far as 100 meters away.
100 meters. That's the length of a football field.
Exactly. An entire stadium, which is basically empty, with all the mass concentrated in one single marble at the center spot.
Wow, okay. That image really sticks.
So now that we have the concept, let's look at the formal relationship, the formula that came from more modern experiments. Could you please read the exact definition from the insert source for us?
Of course. It says, it has been found that a nucleus of mass number A has a radius r equals Ra to the power 1/3, where R equals 1.2 by 10 Al EM equals 1.2 FeM, 1 felometer, 1 felometer equals 10 OM.
Perfect, thank you. That is the money sentence for your exams. Now let's break down that A to the power 1/3 part. That's where the real physics is hiding. A is the mass number, right? Total protons and neutrons.
Yes. So, why the cube root? It seems a bit random.
It's not random at all, actually. It's a very elegant argument about density. Let's build it step by step. First, experiments show that the volume of a nucleus, let's call it V, is directly proportional to the number of particles inside it, which is A.
Okay, that makes sense. More nucleons, more volume, so V is proportional to A.
Correct. Step 2, we know the nucleus is basically a sphere, and the volume of a sphere is 4 by 3 pi r cubed.
Right.
So if V is proportional to A and V is also proportional to r cubed.
And R cubed must be proportional to A.
Oh, I see.
Exactly. And if you just take the cube root of both sides of that relationship, you get that the radius r must be proportional to A to the power of 1/3.
And the R0, the 1.2 femtometers, that's just the constant of proportionality.
That's all it is. And this simple mathematical fact that r is proportional to A to the 1/3 leads us to the most important conclusion about all nuclei.
Which is?
The density of nuclear matter is a constant. It does not depend on A.
Wait, so a tiny helium nucleus and a massive uranium nucleus, they have the same density?
Yeah.
Exactly the same. The nucleons are packed with the exact same efficiency in every single nucleus. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
So what is that constant density value?
It's about 2.3 times 10 to the power of 17 kilograms per cubic meter.
10 to the 17. That number is just, it's unreal.
It is, and we can check it. If you do the calculation for, say, an iron nucleus, Fe56, using its known mass and the radius formula, you get a density of about 2.29 times 10 to the 17. It works perfectly.
It's consistent.
And here's a cool connection. This exact density is what we find in astrophysics, in neutron stars.
Neutron stars, the things left over after a supernova.
The very same. A neutron star is basically a single gigantic nucleus, miles wide, held together by gravity. It's nuclear matter on a cosmic scale.
So a neutron star is essentially the same stuff that's inside every atom. That's an amazing link.
It is. And this whole idea of constant density, it connects directly to our next topic. It's a direct consequence of something called the saturation property of the strong nuclear force.
What's that quickly?
It just means each nucleon only interacts with its immediate neighbors. It doesn't feel the pull of nucleons far away. This short-range interaction is what leads to this maximum constant packing density.
Oh, I see. Okay.
All right, let's shift gears. Let's talk about the silent killers, the common mistakes that cost students marks on this topic. I have 3 main ones.
Okay, let's hear them. This is important.
First one, students assume linear growth. They rate that R is proportional to A. They think if you double the number of nucleons, you double the radius.
But that's wrong. The correction is that R is proportional to A to the power 1/3. Cubic root growth, not linear.
Perfect. You have to say A to the 1/3.
Calm down.
Second pitfall. They assume heavier nuclei are denser. It feels intuitive, right? More stuff packed tighter. So uranium must be denser than carbon.
But we just learned that's not true. The correction is that nuclear density is constant for all nuclei, about 2.3 times 10 to the 17.
Exactly. It doesn't matter if it's aluminium or gold, the density is the same. It's a classic trick question.
Right.
And the third one, students often write that Rutherford's experiment directly observed the nucleus.
But he couldn't have. It's too small. So the correction is that he inferred its existence and size. He deduced it from the scattering data.
Precisely. It was an inference, not an observation. So remember those three. A to the 1/3, constant density and inferred size. Now let's create some memory anchors so this stuff really sticks.
Okay, like a mnemonic.
Exactly. For the formula, just repeat this phrase. A to the 1/3 shapes the nucleus cubic root growth, not linear growth. It tells you the formula and the concept.
That's good, easy to remember. What about for constant density?
For that, there's a physical gesture. Hold your hands close together, fingers pressed tight. That's a small, dense nucleus like lithium. Now, slowly move your hands far apart for a big uranium nucleus. But, and this is the key, keep your fingers pressed together with the exact same pressure.
So the distance between my hands increases, but the pressure of my fingers, the density, stays the same.
You got it. It's a physical reminder that the packing efficiency is constant.
That's actually very helpful. And the final association.
Just the one we started with. The nucleus is the densest thing we know. A marble of it weighs as much as a skyscraper. That's the image for its extreme nature. Okay, let's wrap this up with a final 3-point summary. 3 exam-safe facts you can take away.
Perfect.
1. Nuclei are incredibly small, measured in femtometers, which is about 10,000 times smaller than the atom's radius.
2. The nuclear radius follows the formula R equals R naught times A to the power of 1/3, where R naught is 1.2 femtometers.
And 3. Because of this relationship, the density of all nuclear matter is a constant, roughly 2.3 times 10 to the power of 17 kilograms per cubic meter, independent of the size of the nucleus.
That's a great summary. Very clear.
To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam.
That's ProfSam.com. We will see you in the next deep dive.